A pleasant morning to all of you. My name is Abhilash Gopalakrishnan, and I have spent over 2 decades in architecture and design of software systems. Here, what we are going to discuss is a very important topic which many of our friends have asked questions about, particularly modeling, simulation, and majorly UML in context. We have tried to use a demonstrator and try to explain the key considerations and how it can transform our future. Hope you will enjoy. It's very important to understand how we consider design and experimentation today. On one side, we can look at ourselves, designers, architects, software engineers, or any kind of engineers, looking at how we can satisfy the concerns of our stakeholders, how we can be of making great user experiences which delight our end users, how really we can design for future, because all of us know by the time we provide a solution, probably many others would have thought about it and maybe it's already there. So, and many of the libraries we use could become obsolete. On the other side, we have business leaders looking at how can we innovate and experiment faster so that we can avoid the risk that another competitor or incumbent might bring to the table. And how can we enter new markets? These are all very important questions for the world today because the speed at which business really have to move is really at the speed of light kind of consideration. And if the businesses don't move, obviously, like a dinosaur of the Cretaceous period, you could be affected by the asteroid and otherwise called disruption, which can change everything around you. So the only way to survive the catastrophic effects of disruption and probably ride and invent the future is making us more evolvable. When we talk about evolvability, it's more about a consideration like organisms evolve, we should be able to naturally evolve. This natural evolution is something we have learned as a very important perspective. And with this nature of evolution, design and experimentation suddenly changes the way it is and turns continuous. Let's come back to reality. When we talk about modeling, what do we really see as modeling? Most of us would have come across plan of construction of a house. So when we approach an engineer or a planner, they will provide us with different views, with details, some views with the details of the dimension of the floor from a top viewpoint standpoint, another which allows us descriptions from a front view standpoint, where to park the car, where is the doors, where are the ventilation, where are the chimneys, and sort of. Then the objective is to provide different views so that we can provide different users the details about modeling the building itself, and it is represented from different views so that all the details can be understood and depicted. So why do we model a building? It is for us to understand how much space we are going to occupy, or do we have the right kind of entry, exit, say fire considerations around it, or how is it organized? Do we have enough space for living? Is the different rooms organized well and things like that? So when we model and see the plan or the representation, we get to understand, we get to get answers for many of the questions that we have. On one side, it answers some of our questions. It might lead us to more questions. So that is where it is interesting. If we expand further today with the kind of 3D models of the house, the interiors, if we get to model the interiors, these provide us final details into how it looks like. And with this kind of a model, we can simulate how people can move around, how well it is ventilated, which is probably very important in today's world. This is often considered as higher fidelity, so we can continuously expand our models to be highly more relevant, and then they turn out to be simulating more and more. So when you get to modeling and simulation, we are kind of creating a picture of how we can continuously evolve, and more questions get answered at the same time. It could lead to more conversations for us asking more questions. Civil engineering obviously is bounded by the physical aspects, but that's where software engineering is probably not um, limited by the physical aspect, but it is only limited by imagination. So when we look at modeling from a UML unified modeling perspective, a 4 plus 1 model which kind of simulates some of the models, some of these scenarios could be very interesting for us. So in this 4 plus 1 view, we try to create logical view with packages and classes. We provide sequence diagrams representing the interaction between various components over the external world itself as the user. We provide physical view with deployment diagrams and also development views for how the source control is managed or how continuous integration is managed. Let us dive a little bit deeper, trying to understand a washing machine simulator. So, what we have done is we have modeled a washing machine simulator, and what we have tried to give a software representation of a physical entity. So first thing what we have done is a user interface to show how the washing machine would operate. Similarly, we have created a front end or user interface so that you can operate it. So that is where you have a capability to set settings, how whether it's economic mode that we want to select, and then start the operation. So what we do is we first level we try to model, we try to decompose the entity into further smaller parts, small otherwise what we call subsystems. So when we look at a washing machine simulator, we can look at it like there is a user interface, there is a physical model which we are obviously not going to depict in this particular case, control model behind it. So we will try to create a simulator with control model aspects. Let us quickly have a look at this demo. So what we have done is we have kind of created a decomposition, and then we will uh, run the demonstrator to show you how it looks like. So here, as you will see, we have economy mode. We selected economy mode. Now we will start the execution, and on execution on the right hand side, API will start running, and you will see the kind of transition which happens between the states, water collection happening, then opening inlet valve, stopping inlet valve, start. So the different commands executing behind the scenes, which kind of simulates the control model behind it. And towards the end, it will say the entire operation is completed, transition to training, and finally, end of the operation. So what we captured here is important to understand. Kind of what we have done is we have um, we have kind of given a interface to the model using a React.js front end, and we have created a conceptual model which allows us to, using API and its endpoint, we are providing capability to set mode. Then you have the state machine and the commands which are executed through a start API endpoint. So what does it help us? How does it help us, this kind of a model and a simulator, to understand the picture? So as a model, when you look at this picture with kind of also UML diagrams, representations, then it allows us to read, interpret, and implement. Many of the cases, designers or architects need to lead the development with some kind of skeleton or implementation, which is very important. And one of the major capabilities, important considerations of model is an abstraction. So we may not want to model everything, rather those important details which we feel significant to demonstrate the purpose of our model. That's very important for us. So and then the understanding, sometimes accuracy can be high, low. High fidelity can improve us to ask, and maybe it can enable us to ask more questions, what if questions around it, and cost effectiveness and predictiveness as well play a very important role. So models can be descriptive, prescriptive, or executable. That's what we have seen. We have created an executable model which asks us questions back to us and kind of enables us to iterate. The model therefore becomes a very important part of our kitty when we are creating minimum viable products and kind of lean startup approaches. So what we have done is UML representation of the washing machine simulator a little bit more into the detail. So we have done, so there are two parts, two subsystems, mainly the client and the API. And the API is the one holding the control elements, whereas client is mainly a faceplate or a user interface representation, which allows us access to the API. This is basically using a logical view. I have used a tool called Spark Systems Enterprise Architect to model this. And then on the lower end is a sequence diagram. So here you will see the faceplate making a call to the start engine within the engine service, which leads to a post API slash engine endpoint gets called, API endpoint gets invoked, which is leading to the engine controller, start engine. And once you set the context, then the operation is started and all the operations are complete. It says complete. So this is kind of very simplified view of the picture that we represented. But like what we will see here is UML representations that matter. You can have a use case view, but otherwise, which describes the scenarios. Otherwise, what you will really require is a logical view, possibly with packages and class diagrams and sequence diagrams to represent interactions, and deployment diagrams which represent the physical part of it. So the demonstrator itself is there in GitHub in ABHKit WM-Sim API. Again, it is more of a conversation in the design and experimentation that we are looking from the models. Models raise questions and bring clarity. Sometimes these diagrams ask us questions. When we try to describe it, it asks questions back to us, which enable us to improve the modeling concept. Unified modeling language is a general purpose modeling language and it's used for several cases. And obviously, for real time systems, we have a UML profile for embedded systems as well, which is where sequence diagrams are little more specific and shows the cycle at which they operate and the timing consideration. Timing diagrams is also part of the kitty. And concurrency diagrams which represent the processes or the tasks that we run, and the signals like mutexes or semaphores or what, the cues that we represent, all that can be demonstrated in the concurrency diagrams. So, like what we discussed, models and simulations are a major ingredient for you to innovate and lead than just being a tool in the kitty. They influence us as much as we influence them, like Michael Schrage points out in Serious Play. Um, UML is a modeling language. What is more important for us is the way of thinking. Thank you for your kind attention. Have a great day.